I'm not going to, his long list of awards, and I'm just going to highlight one, which is that he won the Milton and Francis Clouser Doctoral Prize for the best university-wide PhD thesis at Caltech, which is pretty impressive. So I think we're all very excited to hear his talk.
Yeah, thanks for the introduction and thanks for coming to my talk. So I'm here to share some of my new ideas with you and hopefully get some feedback. So I'm going to talk about optimization over a graph with application to power systems. So this talk has two components. One is the theoretical component, which is optimization, and the other one is the practical aspect of this with power. So I spent like 10 minutes in power. Then I'm going to talk about abstract optimization with some application in power. And so this talk is based on joint work with 3 research groups. Steve Hollow and Somaya Sujudi from Caltech, Steve Boyd, Eric, and Matt 12. Steve's a student from here, David Shea and Baljan Zhang from UC Berkeley. So on the power side, the idea is that we are given a network like this, and this network is a large-scale physical circuit, like a circuit for Palo Alto. And now we are interested in doing some optimization over the circuit. Optimizations like resource allocation, state estimation, or some scheduling problem. So we are given a network or a physical circuit, and we want to do some optimization. As long as this network is a generic network, like a communication network or transportation network, all these optimizations are easy. But as soon as we move to power, we have to deal with laws of physics. And that introduces some quadratic nonlinearities. So if we write any of these equations, we're going to see that we have to deal with some quadratic equation embedded in each of these optimizations. Like 60 years ago, we had no problem with nonlinearities. Like in Manhattan, which is a populated area, we had 2 generators for 1 neighborhood. So we didn't have a lot of decision parameters. But now, like currently at PJM, which is the largest electricity market in the world, they solve optimization with 10,000 parameters every 5 minutes. And they imagine that like 5 years from now, we're going to deal with curves of dimensionality. So 5 years from now, we have to be able to solve large-scale optimizations, which are also nonlinear and non-convex. So let's just talk about one optimization, which is a fundamental one in power. We've got a bunch of suppliers, which are connected to a bunch of consumers through a physical network. So here, circles are suppliers, generators, and triangles and rectangles are some sort of consumers. And now the idea is that every 5 minutes, I as a grid operator, the forecast of consumers, I'm going to understand how much power each consumer needs. I've got a bunch of generators, and the question is, how much power should I generate by generator? So there's a physical circuit connecting suppliers to consumers. I have a good forecast of consumers, and I want to do a scheduling or planning on the supplier side. This problem is a resource allocation problem, and it's called optimal power flow, OPF. So more precisely, for each node or each bus, like bus number 4, we have some parameters, some circuit parameters. We are EE people, so we are familiar with voltage, current, complex power, active power, reactive power. So for each node of a network, we've got some physical parameters, and we want to do optimization over all these parameters. From a different perspective, we can model a power grid as a dynamical system. So all we are trying to do is to optimize the equilibrium of the network. So every 5 minutes, we're optimizing the equilibrium of the network, and between each interval, there's a different operator trying to control the real-time behavior. So in the optimal power flow problem, we want to optimize, for example, active powers subject to demand constraints and some physical constraints. We have some technological constraints. So as an example, if I have a line, there's no way to transport too much power over the line. But I'm going to convert some of the power to heat, I'm going to burn the line. So each line has a capacity. So we have to satisfy the demand constraint and some physical constraints. That's the OPF problem. And in reality, there are different companies dealing with these problems. ISOs, TSOs, RTOs, utility companies. So there is no single entity in charge of this. There are multiple companies in charge of this. And they deal with this problem for different reasons. For market, for operation, for security, for planning. So there are various reasons to deal with this problem. And they solve this problem on different time scales, from every 5 minutes to every several days. And the thing is that all these companies are interested in optimization in power, but they don't solve the same problem. For example, the utility company has different incentives than ISOs. So problems are similar, but they're different. And they share the same type of non-convexities. Since power flow equations, the laws of physics are nonlinear and non-convex, in reality there are two ways to solve the problem. Either use linearization or try to find a local optimum. So linearization might be good. Like if we do a market 24 hours before operation, I linearize the problem, I get a solution. And it's been shown that that idea works well. And the good news is that the solution that I get from linearization shouldn't be implemented in real time. It's 24 hours before operation. But if it's 5 minutes before operation, if I do linearization, I'm killing laws of physics. Then that solution is not physically meaningful. So if you want to deal, for example, the electricity market 24 hours before operation, we can use linearization. But 5 minutes before operation, linearization kills a lot of physics. And we have to use local stage algorithm. And if we use local stage algorithm, that means we're not trying to find the best solution. Maybe there's a better solution which is global. And in that case, we might be wasting a lot of dollars, billions of dollars. So from theoretical perspective, this problem has been around for 50 years, and 3 different communities work on this: power, operation, research, and econ communities. And from the government perspective, in the past 3 years, every summer, they had a conference on optimization in power. They're really concerned about optimization in power, but they don't know how to solve problems 5 years from now. In that case, they don't know how to do the scheduling and keep the lights on. So in the past 3 years, I tried to do 5 different projects. I give you an overview of the first 3 ones. Then I'm going to talk about the last 2 ones, because some of you might have heard of the first 3 projects. The first project was joint work with Stephen and Lavaei. That's the following. Given an OPF problem, solve it in polynomial time. So I'm given a scheduling problem or a planning problem, and I want to solve the problem in polynomial time. The bad news is that OPF is NP hard in the worst case. Like many other optimization that we see in real world, it's NP hard. But as soon as we move to power, we've got some sort of a structure. Maybe that structure simplifies the problem. So we got a sufficient condition under which there is a way to find a global solution. And we decided to check our conditions on some synthetic data and some real-world circuits corresponding to Midwest US. And also some people at IBM did simulation on European grid, and Southern California grid did a lot of simulations. And the good news was that that condition was always satisfied. So we have a problem, and if we design the coefficient of the problem in such a way that we're allowed to do it, that problem is NP hard. We can make it as complicated as possible. But if we get the coefficient of the problem from real data, then that problem is polynomial time solvable. Or that problem can be convexified according to the test system that they've tried. But that was kind of strange. We decided this to see what's going on. And we noticed that everything was related to the physics of a power system. Like if I have a power line, that means the lumped model has 2 capacitors, 1 inductor, 1 resistor. And that gives me some hidden structure on the coefficient of the optimization. Maybe that hidden structure simplifies the problem. So in project number 1, our conclusion was that practical problem may not be hard. In project number 2, which was joint work with Somani Sujudi from Caltech and David Cheney, the student from UC Berkeley, we tried to have a more or better characterizations of when optimization is easy, when optimization is hard. So we work on the graph. We noticed that if we do optimization over acyclic graphs, optimization is easy, OPF is easy. If we have cycles, optimization might be hard, but there is a way to fix the problem. So we tried to study different topologies. We noticed that optimization, like OPF optimization, is closely related to the topology of a power network. If we are doing optimization at the distribution level, optimization is easy. If we are doing that at the transmission level, it's hard unless we have enough power electronic devices. So we try to study the physics of power network. So I'm not going to talk about project number 1, 2, and also project number 3. These are just some overview of the results that we got in the past 3 years. Project number 3 was joint work with Steve Boyd and 2 of his students. And the idea is the following. If I'm a control person sitting in a control room, or I'm a power engineer sitting in a control room, I don't care about polynomial time solvability. I need to do the scheduling for a part of the US in 5 minutes. So I need to get a feasible solution in 5 minutes. If the solution is local, it's good. If the solution is global, it's even better. So we want to be practical. We want to have a parallelizable algorithm for solving the problem. We noticed that if you want to do optimization in MATLAB, which is an educational software, then it's pretty slow. If we have 10,000 parameters, we get a solution in 6 hours. But there is a way to speed up the process. And OPF has a lot of good structure that if we can exploit it, we can solve the same problem in less than 1 second. So his student wrote a custom solver for this, and notice that there is a way to simplify optimization. So these are 3 projects about power. But I'm going to talk about project number 4 and 5. So project number 4 is more about optimization. So from now on, we want to talk about optimization. So far we have learned that maybe there's something in power which simplifies optimization. But what happens to other optimizations? What happens to other physical systems? So the idea for the project number 4 is the following. I'm given a physical system. It could be photonics, it could be material, it could be power system. I define an optimization over that physical system. Then that physical system gives me some hidden structure of the optimization. And we want to understand how does that hidden structure make optimization easy or hard. So we want to relate the polynomial time solvability of abstract optimization to some structural properties. And project number 5 is related to a problem in CS, which is called generalized network flow. So I'll get to that later. Let's focus on project number 2. We want to connect polynomial time solvability to some structural properties. So instead of starting with complicated theorems, let me just work through examples. So abstract optimizations are hard, but when we go to the real world, we've got a lot of structures. Like in power system, we have 2 kinds of structures. We have a sparsity, meaning that a power system has a planar graph. In other words, the number of power lines is linear in terms of the number of buses, it's not quadratic. And these kinds of sparsity has been exploited in CS, but not in optimization. But this kind of sparsity doesn't make an NP-hard problem polynomial time solvable. We have to deal with more sophisticated structure. So the idea is that we want to see how non-trivial structure make optimization hard or easy. So let me start with 2 examples. In example number 1, which is an abstract optimization, we want to minimize a polynomial with 2 parameters, x1 and x2. We want to minimize x1 to the power 4 plus a x2 squared plus b x1 squared x2 plus c x1 x2. A, B, C are given coefficients, and at this point we don't care what values they've got. Now we can see that there is some sort of structure in this polynomial. We don't have all possible monomials for a polynomial of degree 4. For sample values of the coefficient A, B, and C, this polynomial looks like this, which is not convex. So I want to minimize the polynomial with 2 parameters. The problem is easy because they've got just 2 parameters. There are many ways to solve it. But since this polynomial is not convex, the problem is not trivial. We want to come up with a convex optimization which solves this. So I hate to deal with the polynomial of degree 4. I hate to deal with higher order of polynomial optimization. I can make it quadratic. There's a famous method for doing this. We can write x1 to the power 4 as x1 squared to the power 2. And we can define x1 squared as a new parameter x3. Now x1 to the power 4 is x3 squared. So we can convert all higher order terms to some quadratic terms. In that case, by introducing 2 new parameters, x3 and x4, everything looks quadratic. So instead of dealing with the high order optimization, polynomial optimization, we can equivalently deal with the quadratic optimization. Now again, at this point I don't like to deal with quadratic terms. I can further simplify the problem. If we consider x as the vector of parameters, x1, x2, x3, x4, the problem is quadratic in x, but it's linear in the matrix x, x transpose. X is a vector of parameters, x, x transpose is a matrix of quadratic terms. So if I replace x, x transpose by new matrix W, then everything looks linear in W. Quadratic in x is linear in W. In other words, I'm just replacing a quadratic term like xij by a new term xwij. I made it linear. But I'm losing too much. I'm going from a vector space to a matrix space. I'm going from x to W. That W is a structure. For example, that W is the inner product of 2 vectors. It must be positive semi-definite. I explicitly impose this constraint. This new optimization is called SDP relaxation. SDP stands for semi-definite program. This problem is easy, it's convex, That problem is non-convex. That's easy because we have two parameters. I solved this problem. If W has optimality as rank 1, then it can be written as the product of two vectors, then all these optimizations are equivalent. So we would say STP relaxation works if there is a rank 1 solution W here. And the question is, for what values of A, B, and C, we have a rank 1 solution W? So the idea is the following. I work on quadratic optimization, I map it into a graph. I identify the cross terms. Cross terms like xi, xj, where I is not equal to j. And I map it into a graph. I make it in a trivial way. I connect, we have 4 parameters, x1, x2, x3, x4. I put 4 vertices. I connect vertex I to vertex j, xi, xj shows up in the optimization. And I put the corresponding weight, corresponding coefficient as the weight of the edge. Now the claim is, as long as this graph is acyclic, STP relaxation works. For all values of A, B, and C, this graph is acyclic. So there was a hidden structure into that optimization. And because of that hidden structure, which is evident from this graph, if you solve this problem, you're going to get the rank 1 solution. So that's the first idea. Due to the structure that we see in this graph, there is no cycle here, it's guaranteed that we have a rank 1 solution. Now let's make it more complicated. Add constraints to the polynomial optimization. Say we have a number of constraints. And each constraint says that a polynomial should be less than or equal to a constant number. And we assume that each constraint has the same structure as the objective. Now the challenge is that we cannot have a weighted graph in the regular sense. For example, the monomial x1 squared x2 shows up multiple times. That means that for a cross term might show up multiple times with different weights. In that case, instead of having a weighted graph, we have a new thing that we call a generalized weighted graph. We identify the cross term, the quadratic optimization, draw the graph. Xi, xj shows up multiple times. I put all the corresponding coefficients in a set, and that's going to be a weight set corresponding to a cross term xi, xj. If two things happen, STP relaxation works. The first one is that this graph should be acyclic, which is always true. And the second one is that each weight set should be sign definite, meaning that all VI's should be positive or negative, all CI's should be positive or negative. So as long as the topology of the graph is acyclic and each weight set is sign definite, STP relaxation works. So that's the strange thing. There's some sort of hidden structure into that optimization. By looking at this graph, we can make some conclusion. Now the question is, what happens if some CI's are positive and the rest are negative? The set may not be sign definite. But we've got an acyclic graph. Maybe having some sort of acyclic graph simplifies optimization to some extent. So what happens if the sets are not weight, sets are not sign definite? So if we solve the STP relaxation, the rank of W could be anything from 1 to n. If it's 1, STP relaxation works. There's some work with some CS people at Princeton University. They've shown that the rank of W, the generic rank of W is square root of n. It depends on the size of the optimization. But we can show that as long as this graph is acyclic, it's guaranteed that we have a rank 2 solution. That's the strange thing. There is some sort of hidden structure here, and that hidden structure means that this graph is acyclic. As long as this graph is acyclic, there is always a rank 2 solution, and that's hidden. Meaning that if you get some sample values for the coefficients and solve it in MATLAB, you get a solution whose rank is a square root of n. But we have an infinite number of solutions. There's a solution whose rank is 2, but there's a way to get it. And comprehending the ideas of regularization may not help you to get this. There's a different way to find this. We'll get to this later. So in example number 1, we translated the structure, the hidden structure of a polynomial optimization into a generalized weighted graph, and by looking at the topology and the weight set, we made some conclusions. And now the other thing is that since the rank of W is 2, doesn't depend on n, one would say maybe the problem is easy, we're done. STP relaxation doesn't work, but there's a different method which works. But we can show that going from rank 2 to rank 1 is NP hard. The problem is NP hard, like 90% approximation works. We have an approximation ratio, it's not epsilon approximation. So we make it more clear in this talk. So that's example number 1. In example number 2, the famous optimization is quadratically constrained quadratic optimization. We minimize the quadratic term subject to a number of quadratic constraints. To comply with the previous example, assume that the generalized weighted graph is acyclic. We get to the cyclic case later. So we identify the quadratic terms like x, y, x, j, draw an edge, I put the corresponding coefficient into a weight set. There are multiple cases. The optimization could be real valued or complex valued. Assume that that's real value. X is real, coefficient m, i's are real. In that case, it's guaranteed that there's a rank 2 solution. If you solve the problem in MATLAB, you might get a solution with rank in the square root of n. If you try to use regularization to reduce the rank down, then you may not be able to get a rank 2 solution. But there's a different way, which is polynomial time algorithm, to find the rank 2 solution. So the interesting case for me is not the real case, it's the complex case. Because people have already shown that, like if you consider max cos, it's hard in the real case. As soon as we go to the complex domain, magic happens. So you want to talk about complex case, and that's more related to power. What happens in the complex case? Complex case means the x that we are looking for is complex. The interesting thing is that as long as the coefficients are real, SDP relaxation works. So that's the first result. I have an optimization with real coefficients, with complex x, and an acyclic graph. That's some sort of hidden structure. SDP relaxation works. Or if the coefficients are purely imaginary, again, SDP relaxation works. But the idea is that what happens if the coefficients are general complex numbers? So MJs are just Hermitian matrices, MX. So if M is real matrix, X is a complex number, you're done. SDP relaxation works. But if M is a general Hermitian matrix and X is a complex vector, SDP relaxation may not work. You have to talk about sign-definite sets. How can I generalize the notion of sign-definite sets from real case to complex case? I have a bunch of numbers. I can say if that set is sign-definite or not by saying if all numbers are positive or negative. What happens if I have a bunch of complex numbers? We have to generalize this notion to be able to deal with this case. Any questions so far? So in the real case, we would say a set T is sign-definite if all elements are positive or negative. How can I have a meaningful generalization of this to complex domain? So let's look at the problem from a different perspective. If I have a bunch of positive numbers, its mirror is a bunch of negative numbers. Now 0 is the separation between set T and minus T. So we do the generalization in the complex domain like this. We would say a set T is sign-definite if T and minus T are separable in R2 via a line. Let's see what this means. Assume that we have a set T with 4 complex elements. Each complex element corresponds to a point in R2. So a set T means, for example, in this case, 4 points. And the set minus T is mirror image in another 4 points. If there is a line separating T from minus T, then you would say the set is sign-definite. In the first case, it's sign-definite. In the second case, if set T looks like that, T and minus T are mixed. There is no way to separate them out by a line. If we go by this generalization, similar of the result that we have in the real case can be generalized to a complex case. That's a surprising thing. So let me start with the real case. Let me just formalize the problem. We want to do an optimization in X, but the argument of optimization is not X, it's Y and Z. So we want to minimize f naught of y and z, subject to the constraint that fi of y and z is less than or equal to 0. So the parameter of interest is x, but the optimization is written in terms of y and z. So let me tell you what y and z are. Y is the set of quadratic terms in one variable. Z is the set of quadratic terms in 2 variables. So y consider just quadratic terms in xi, z consider clusters. So the idea is that if we consider that optimization, its argument is nonlinear in X. Its argument is quadratic in X. And we wanted to deal with that quadratic argument. Now we have some sort of a structure on Z. Not all cross terms are important. And if we have a cross term like xi, xj, it might show up multiple times. We have multiple weights for that. Cij1 up to Cijk. So now what we want to do is to do SDP relaxation on Y and Z. Y and Z are quadratic in X. We can make them linear in a matrix W. And the question is, under what condition does SDP relaxation work? And we don't want to even assume that FIs are convex. They're arbitrary functions. So we have an optimization whose argument is quadratic in X. We want to make it linear by using STP relaxation. STP relaxation is not the same as convex relaxation because we don't assume that Fi's are convex. But for some of the results, we need to assume that Fi's are increasing. So I make this assumption up front for all results. Fi's are increasing in quadratic terms. So we assume that Fi's are increasing in quadratic terms. Now we can capture the structure of the optimization by a generalized weighted graph. I look at Z, I identify cross terms. If I have a cross term, I have an edge. I look at possible coefficients for X, Y, X, J. I form a weight set. And the question is, for what graph does STP relaxation work? So that's the setup of the problem. Let me start with the real case. The real case is like this. We have a generalized weighted graph. Each edge has a bunch of real numbers. So first of all, we need to assume that each weight set is sign definite, meaning that all numbers are positive or negative. So we assign a sign to each edge, +1 or -1. Now if two conditions are satisfied, STP relaxation works even if Fi's may not be convex. We need to satisfy one condition for each edge and one condition for each cycle. So we allow cycles, but we need to satisfy some cycles. The condition for edge is that each weight set should be sign definite. The sign should be +1 or -1. It shouldn't be 0 or sign indefinite. And the condition for cycle is that if we have a cycle, if we go around the cycle, we have a bunch of +1s and -1. The number of +1s should be an even number. So if I go around the cycle, the number of +1s should be an even number. So if we satisfy one condition for each edge and one condition for each cycle, STP relaxation works. So there are some sort of special cases of this theory. Like for acyclic graphs, there is no cycle to be worried about. The only condition is that all sets should be sign definite. For bipartite graph, as long as all coefficients are positive, optimization is easy. For arbitrary graph, as long as all coefficients are negative, optimization is easy. And this was a paper published in 2003 in optimization literature. So the last case was a special case already published in 2003 by not considering graphs, but by talking about negative optimization. So now the other thing is that what happens if some of these conditions are not satisfied? For example, in the acyclic case, what happens if sets are sign indefinite? I have an optimization, the topology is captured by a graph, and that graph is acyclic. Maybe that tells me something. Then we can show that there's a solution whose rank is 2. If it's 1, STP relaxation works. If it's not 1, then the solution whose rank is 2. I can start with that one, use approximation. Some sort of approximation ratio. And we can generalize this to bipartite graph. There's a large class of optimization which have a rank 2 solution, even if they don't have a rank 1 solution. So before moving to the complex case, let me just mention something. When I was talking to some MIT people, they said, maybe optimization over acyclic graph is easy. We didn't talk about computational complexity. We just said under what condition does STP relaxation work. So the bad news is that optimization is hard even over acyclic graphs. People who work on dynamic programming already know that. Some optimization is easy over acyclic graph, but that graph is different from the graph that we consider here. For example, if we consider an optimal control problem, the X state of a system depends on the previous state of a system. That gives me a tree of evolution. And that gives me a tree for Markov chain. And as soon as we have tree, dynamic programming works. So this graph is different from the graph that people consider in dynamic programming. Optimization over acyclic graph is hard. Let's see why. The idea is easy. Number partitioning problem is an NP-hard problem. And the idea is this. We have got a bunch of numbers, alpha 1, alpha 2, alpha n. We want to add or subtract them in such a way that the overall expression becomes 0. We've got a bunch of numbers. The question is there any way to add or subtract these numbers so that we eventually get 0? So let's convert this problem to an optimization. Instead of the signs which are supposed to be +1 or -1, I define some optimization parameters, xi. Sum of alpha I xi should be 0. xi squared should be 1. And that's a feasibility problem, so I add the trivial objective 0. Now the first constraint of this optimization is linear. We make it quadratic. We want to deal with quadratic terms so that we can move them into a graph. How can I go from linear constraint to quadratic constraints? Easily, we use the lifting idea. We introduce a new parameter x naught, so that x naught squared is 1, and multiply the linear constraint by x naught. Now everything is quadratic. And the other thing is that now the first constraint is quadratic, but it's equality constraint. I want to make it an equality. Again, the idea is easy. The left side should be less than or equal to 0, and negative minus the left side again should be less than or equal to 0. So that's the quadratic optimization that we care about. Let's capture the topology, the structure of this optimization by graph. The graph looks like this. The new parameter x naught is connected to all existing parameters, and each edge has a weight set with two elements, alpha I and minus alpha I. And that implies that optimization over this graph, which is a sparsest graph that we can imagine, is NP-hard. We have a star graph. We are very sparse in the topology, but also sparse in the elements. We have two elements in each set. So optimization over acyclic graph, with just a few parameters in each weight set, is hard. But as soon as we have got some properties like sign definite sets, we can then make the problem polynomial and solvable. So this is a story about the real case. We need to satisfy one condition for each edge and one condition for each cycle. Now let's go to the complex case because that's related to power. In this case, we need to assume that the weight sets are sign definite in the complex domain, meaning that the set T and minus T are separable by a line. And this result, for example, this could be one graph. We have a graph, each weight set has a bunch of complex numbers, that set should be sign definite. And the result that I'm going to talk about now is a generalization of the result that Manichandi, Steven Lu, and 12 of the students got last year at Caltech. They work on this quadratic optimizations with positive semi-definite objective. Then it turned out that we can generalize that to arbitrary polynomial optimization, and we don't even need to assume that the objective is positive semi-definite. So the result is the following. Optimization is easy, or SDP relaxation works for acyclic graph as long as the weight sets are sign definite. This is in the complex domain. And it turns out that this corresponds to optimization over power system at the distribution level. The OPF problem that we introduced at the beginning of the talk is related to this part. Optimization over acyclic graph is sign definite complex sets. So there are some special cases of this. For example, assume that the graph is acyclic, but the weight sets are real numbers. I have a weight set consisting of a bunch of real numbers. If I have a bunch of real numbers, that set may not be sign definite with respect to R, because some of them might be positive, the rest negative. But every real set is sign definite with respect to C. According to our definition, if you have a bunch of positive or negative numbers, that set is always sign definite with respect to C. And that implies that if the coefficients of the optimizations are real numbers, but the parameter of the optimization is a complex number, then optimization is easy. The other extreme of this is that what happens if the weight sets are sparse? If each weight set has just one or two elements. We can show that every set with one or two elements is always sign definite. If I have just 2 points, I can ensure the mirror of that there's always a separation. So optimization in the real world are really sparse in two senses. In terms of the topology, and in terms of the number of times that each element appears. Like in power, each cross term appears 10 times independent of the number of losses in the network. If that was true, the problem was trivial. So this is one result about acyclic graphs. So what happens to cyclic graph? Cyclic graph for complex optimization is a little tricky. And this is a generalization of the result that David Shea and his student got last year at UC Berkeley. They work in power for some special cases, but I'm going to talk about the general case. But the idea is that in power, if we have lossless lines, all the coefficients of the optimizations are purely imaginary. And now the question is, if we have an optimization with purely imaginary coefficients, is that optimization easy or not? We have a standard optimization with real coefficients, with general complex coefficients. But it turns out that optimization with purely imaginary coefficients is easier than optimization with real coefficients, and it's easier than optimization with general complex coefficients. So for example, if each weight set has a bunch of purely imaginary numbers, which are homogeneous, meaning that the imaginary parts are all positive or negative. Optimization is easy as long as the graph is weakly cyclic, meaning that we don't have a lot of cycles. So we allow cycles in the graph. So optimization with purely imaginary coefficients is easy. And one would say, okay, this has application in power because transmission lines are mostly lossless. How can I use this for abstract optimizations? What is the chance of getting an optimization whose coefficients are purely imaginary? The idea is that if I have an optimization whose coefficients are purely real, I can multiply that by I. Maybe there's a way to make it purely imaginary and use this result. So one example could be like this. It's the famous problem which is called max phase. Assume that they've got a bunch of numbers whose norm are 1. We want to do optimization over the phase of that number. I've got a bunch of xi's, which xi is a complex number, its norm is given. But we want to do optimization over phase of x. So as an example, assume that the objective is quadratic in x, and this matrix M is real. It makes sense to assume this matrix is real. The question is, under what condition does STP relaxation work? We can make M purely imaginary, as opposed to real, just convert the problem equivalently, and to conclude that STP relaxation works for this max phase problem, as long as the graph corresponding to M is weakly cyclic and bipartite. So we can talk about like an abstract optimization through some generalized weighted graphs. And this was one of the hardest things that I tried to prove in my life. Even the special case in power, the Davis-shaped proof was quite non-trivial. But once we have done with proving that optimization with purely imaginary coefficient is easy, we can talk about optimization with just the real coefficients. So now let's move to power, see how we can use these ideas in power. The optimal power flow problem looks like this. We have objective, we have several constraints, we have capacity constraints. The last one is called power balance equations. So this is one problem that we care about in reality. That's the most fundamental optimization in power. We have objective. In terms of the power that we want to generate, we have a lot of operational constraints. We have capacity constraints. And the last one is called power balance equation, which is conservation of energy. Meaning that whatever power I input the network goes through the network, doesn't disappear. But for now, assume that we change the formulation a little bit. People who work in optimization already know that nonlinear equality constraints are bad. Make them nonlinear inequality constraints. Assume that you're allowed to replace this equality constraint by an equality constraint. At this point, I'm not going to talk about what happens to the solution, but assume that we're allowed to change the formulation a little bit. Then if you look at the problem, we can see that we have quadratic terms. VV transpose, V is a vector of variables. We've got VV transpose in natural way. It's quadratic. Now we have learned how to use STP relaxation. We replace VV transpose by a new matrix W. Impose the constraints that W is positive semi-definite. After solving this convex problem, if we're lucky and we find the rank 1 solution, we're done. And the question is, under what condition does STP relaxation work, leading to a rank 1 solution? So there are 4 cases in reality. OPF could be over DC lines or AC lines, meaning that the optimization is real values or complex values. And in terms of the topology, we could work on distribution network to transmission network, meaning that the graph is acyclic or cyclic. Now we can imagine 4 cases: DC distribution, DC transmission, AC distribution, AC transmission. Out of those 4 cases, STP relaxation works in 3 cases: DC or AC distribution and DC transmission. So there are 4 cases in reality. In 3 cases, STP relaxation works. It's DC or AC distribution and DC transmission. Let's see why. We're able to generalize the idea. We may not want to work on just one specific formulation of OPF. Make it very complicated. Just the arbitrary increasing functions of active powers, reactive powers, voltages, any arbitrary things. So you can see that the challenge is to deal with quadratic terms. These functions are not that problematic. The question is, how can we get rid of quadratic terms? So let's talk about quadratic terms. 2 buses are connected to each other, so 2 nodes in a network via an overhead cable, an underground cable. Now we have powers from different directions. We have quadratic terms if we write laws of physics. And the question is, how many coefficients have we got in this optimization? About 10 coefficients. Each coefficient is a complex number. We can put a point corresponding to that. So for each line, there are some cross terms, x, y, x, j, and we have a weight set. That weight set has 10 elements. And the question is, what's the location of those points? We can show that since the system, first of all, we have 10 elements, and second, since the system is passive, meaning that I transport power over a line, I dissipate power and do not generate power, all these points are in the left half plane. So if we regard an optimization as a dynamical system, the modes of the optimizations are in the left half plane due to passivity. So we can show that if we have an analogy between optimization and dynamical system, we have some notion of stability. All coefficients of the optimizations are complex numbers in the left half plane. This set is sign definite because the image of this one is the left half plane, the right half plane, and the imaginary axis is separation. So that's the magic happening in power. Due to passivity, we have sign definite sets, which are complex sets, and that makes optimization easy. So weight sets are sign definite. So in 3 cases, we are safe because of these properties. And the proof is based on defining some cones. We define some cones for a set of coefficients. We consider the mirrored cone. We work on the cones showing that since there is a separation between these 2 cones, SDP relaxation works. So what happens to the 4th case, AC transmission? We can show that there are counterexamples. AC transmission is a case where the problem is NP hard. So there's a boundary between problems which are easy and problem hard. And identifying that boundary is hard. But as long as we have enough number of power electronic devices into the network, which is called phase shifter, then optimization is easy. There's a transformer which has been used in reality for many years for a different purpose, for relieving congestion. And this result shows that if we have that kind of transformer in the right location, then optimization is easy. And the other thing which was collaboration with Steve Boyd was that, like, so far we talked about polynomial time algorithms. But that doesn't mean that it went from a vector X to a matrix W, if you have 10,000 parameters, the convexified problem has 10,000 squared parameters. So we have a curves of dimensionality given the computational power. Let's use the fact that, for example, if a power network is a plane that is structured, then we can use the idea of like message passing and showing that the same optimization can be solved quickly. So now, given that the problem is convex, there is a way to exploit the structure, the sparsity structure of the physical network to simplify the optimization. So far I just did, we changed one constraint. We changed equality to inequality. So what's the interpretation of this in reality? The Lagrange multiplier for that equality is the price that you pay on your electric utility bill. So normally you suppose that you're using electricity and you have to pay for electricity. So you assume that the Lagrange multiplier for that equality constraint is a positive number. That's why changing equality to inequality doesn't change the solution. In reality, it happens that that Lagrange multiplier is negative. They dump power, or some people are paid to get power. Because some lines are congested, we have to have power balancing, and due to the physics, we either have blackout or someone should get power for free to do the balancing in the network. So that assumption that you're allowed to change equality constraint to inequality constraint at the beginning corresponds to the assumption that we sell power at a non-negative price. So what happens if you want to go around that assumption and start with the original formulation? Then algebra doesn't help much. We have to talk about geometry. Because SDP relaxation doesn't work, one would say maybe there is a different algorithm which works. So we're talking about numerical algorithm. But as soon as we're able to identify the feasible set of the optimization, and if we understand where the solution is going to be, then we can talk about what kind of algorithm is able to get us to that point. So let's talk about the feasible set. For example, what's in a 3-bus system? What's the feasible set for P1, P2, P3? There are 3 injections. These injections are not arbitrary. I can inject different values of power at different points of the network. They should satisfy the laws of physics. For example, if the network is lossless, the sum of Pi should be 0, and they should satisfy voltage constraints. The feasible set for this system looks like this. It's a twisted surface. It's a very complicated surface. And the question is, how can I do optimization over a twisted surface? So if we assume that the objective that we want to consider is increasing in Pi's,
then not every point in the feasible set is qualified to be a solution. If I have a complicated feasible set, the objective is increasing. In that case, the solution should be on the front of this non-convex object. So let's take the front of this, or the further front of this out. The front of this complicated twisted surface is something easy. Now, if there is a convex object whose front looks like this, I can do the optimization over that convex object. So that's the convexification idea, independent of what kind of numerical algorithm we want to use. So, and if the front is non-convex, no matter what we want to do, if we don't use left-wing ideas and don't change the number of parameters, there is no way to get that using convex optimization. So we can talk about the geometry. And then we can see that there is a way to do this. The front of this is the front of a convex object if some condition is satisfied in terms of the reactance and resistance of a line. And then and that means that if you have two buses in the network, there are two complex parameters. Each complex parameter has a phase, has a magnitude. The difference of the phases is called relative phase. That relative phase should be less than 45 degrees. In reality, we never go more than 10 degrees. That's the stability limit that we have. So we are really using the physics. We are saying that the physics, the stability limits, the reactance, and the resistance of the line that we have designed using physical material, simplified optimizations. So that's the power story. Let's go to CS problem. I talk about this in just for 5 minutes. There's a famous problem called network flow. And if you've taken a convex optimization course or some CS courses, you have came across this. The idea is simple. We have a commodity of interest. It might be power, water, or gas. We don't care. We inject some certain values of that commodity. Then we get some injection, we get some flows. And what we want to do is to do some optimization over injection. So we want to minimize some of Fi's of Pi, these are injections. So forget about power, this is a general problem. And then injection is sum of flows. If you do injection, the injection is going to be a split between different branches. They have some flows. The complicating constraint is the following. If I have a line, I have injection from both ends. The network flow problem assumes that the line preserves the flow. If I have water being injected into the line, it goes through the pipe without changing anything. And that means that like Pij is minus Pji. That's the network flow problem. In 1995, around 1995, people can start generalized network flow. And the idea is that we need to allow some losses in the network. We might lose a part of the commodity that we're sending through that line somewhere in the core of the network. And they showed that if the loss is a linear function, there's a linear time algorithm for solving this. So if they studied the linear loss case, what happens if this loss is nonlinear? In power, it's quadratic. In power, if you write the loss here, we can see that this loss is quadratic in power. So Pji is a function of Pij. And each injection has lower and upper bound. So that's the problem. For each line, we have a complicating constraint saying that the flow at one end is a function of the flow at the other end. We just make one assumption, or maybe two assumptions. Fi should be increasing, Fij is decreasing. Let's see what this means. If I increase this injection, it's expected that the cost increases. If I increase the input, it's expected that if I increase the input, it's expected that the output increases. And that means that Fij should be decreasing because of the direction. So these are natural assumptions. Fi's are increasing, Fij's are decreasing. We make one more assumption that these are convex functions. In power, it naturally happens. The question is, under what condition can I solve this problem in polynomial time? So it's some sort of generalized network flow problem. We don't make any further assumption on Fij's. For example, we just consider two parallel lines. We have P1, P2. The feasible set for P1, P2 could be quite complicated. Could be this, could be this. So the feasible set is non-trivial. We have a lot of phases which are non-convex. How can I do optimization over this or this object? So let's talk about the convexification approach. Pij is function of Pji, or Pji is a function of Pij. It's the equality constraint, make it an equality constraint that's convex, it's trivial. Then we show that something strange happened. If we do it this way, the convexified problem always gives us the correct injection but wrong flows. That's one thing quite unnatural. For example, in the context of STP relaxation, I solve an STP relaxation and I get a W. If its rank is 1, I'm done. If its rank is not 1, it means that STP relaxation doesn't work. But here it means that if the rank of W is not 1, a part of the solution can be recovered from W. So, convexification on generalized network flow problem always find the correct injection but wrong flows. But the good news is that as soon as I've got the correct injection, there's a different method for finding correct flows. As soon as I know how much power I'm injecting from different points in the network, there's a way to find the flows. That's the unique mapping that we can do it. So that's the thing that we can do in generalized network flow, which is a little bit strange in optimization. I skip this, it's a little complicated. So let me just wrap up the talk. The motivation is that there are problems of optimal power flow that we solve every 5 minutes in reality. We do it for 2 purposes. If I'm the grid operator, I have to do the planning to keep the lights on, to send power. In that case, I care about the feasible solution. If I'm a utility company, I deal with consumers, I like to find the best solution to reduce the bill. And this problem is non-convex. And we have a lot of parameters, nonlinear, non-convex, that we want to see how we can solve. I can contrive the coefficients to make the problem very complicated. But we observe that if the coefficients of the optimization come from real data, STP relaxation works in the right coordinate. So we try to come up with some sort of notion of optimization over graphs. We have an optimization whose argument is quadratic in X. We want to make it linear maybe in W. In order to be able to see under what condition this idea is feasible, we just capture the structure of the optimization by a generalized weighted graph. We have a graph, each line or each edge of the graph has a weight set. There is an interplay between the topology and the weight sets, and that makes optimization easier or hard. Then we can talk about several classes of polynomial time optimizations. Like, what are the special cases where we care about, and as a result of this idea, that optimization is easy. And in a very different direction, we have a generalized network flow problem. That's a CS problem. We talk about the general commodity. We notice that, for example, if you use STP relaxation, we always get a high-rank solution W, but the part of the solution can be always recovered from that W. And given that part of the solution, there's a different algorithm for recovering the whole thing. So convexification on generalized network flow gives us correct injection and line flows. But once we have the correct injection, there is a different algorithm for finding correct flows. And also in the context of power, we have passivity in lines. We have suppliers generating power. We have consumers which need power. We have a big network, physical network for transporting power. We never generate power inside that network. So it's a passive network. That passivity simplifies everything. That gives us time definite sets. Okay, thank you. I'll stop here. I'll be happy to take your questions. Any questions? Okay, thank you.